Good morning, dear students. In the previous class, we had begun deriving the element body force vector. This is the expression for the work potential due to the body force work potential due to the body force. So here minus indicates because the work potential due to body force is the work done by the external force. The work done by the external force is considered negative. So therefore the work done due to body force is minus integral over the length of the solid u transpose FA into dx. Now for an element, so we take the expression like this and we expand using the displacement u equal to n1 q1 plus n2 q2 into dx, and this you can write like this. We saw in the previous class how this expression becomes like this. So later the global coordinate x was converted into natural coordinate, hence in place of dx you can write LE by 2 into dj. Now we have evaluated in the last class each shape function with respect to the global coordinate x. The global coordinate was converted into natural coordinate, and integral of n1 dx over the length of the element, it was obtained LE by 2 over the length of the element, it was obtained LE by 2, and integral over the length of the element n2 dx, how it was obtained LE by 2. Therefore we can understand that integral of Ni into dx, which equals to length of the element by 2, and integrate this over the length of the element. So now if you draw a plot showing the variation of the shape function with respect to length and determine its area, you get LE by 2. Therefore integral of Ni dx represents the area of the right angle triangle. This is the right angle triangle. So what we have, when you see the variation of the shape function with respect to length of the element. Okay. Now integral over the length of the element u transpose F A dx, which equals to q transpose AE by 2 LEF into a column matrix having the elements 1. How you get? Because so here integral of n1 dx equals to LE by 2. Understand? How this q transpose comes into consideration, because that u equals to a row matrix having the elements n1 n2 into a column matrix having the elements q1 and q1. This I represent by the shape function matrix n, and this by q. Therefore u transpose equals to q transpose into n transpose. The q transpose comes out. Right? This n transpose is a column matrix, we know, having the elements n1 and n2. Hence when you integrate each with respect to dx, you get LE by 2. Okay? So q transpose, it comes out. A is the cross section area of the element. AE LE by 2 into F is the body force per unit volume, it is constant, and into a column matrix having the elements 1 and 1. Now this, if you compare with the form say Q transpose into some bracketed term. This bracketed term I say FE. FE. So what is FE? Therefore FE equals to AE LE F by 2 into a column matrix having the elements 1 and 1. What is AE LE F here? It indicates the body force of the element, finite element, which is how, if you rewrite this matrix, for example, if you rewrite, how it appears? It appears like this, a column matrix having the elements AE, LE, FE by 2, again AE, LE, FE by 2. Okay. These elements correspond to the degrees of freedom 1 and 2. So when you take a one-dimensional element connecting two nodes, say 1 and 2, okay, the node 1 has 1 degree of freedom, say Q1, and node 2 has another degree of freedom, say Q2. AE, LE, FE by 2 is half the body force, and AE, LE, FE by 2 is half the body force. So what we can understand from this matrix, we can understand that the total body force is equally shared by both the nodes. Is equally shared by both the nodes. If you have a solid like this, for example, with uniform cross section, right? Say L is the length of the solid, A is the cross section area, and F is the body force per unit volume. What is the total body force? ALF, right? Now I say this is node 1 and this is node 2. Considering the entire solid as one element, the total body force is equally shared by both the nodes. Therefore, I can understand that at node 1, we can consider a body of weight AF by 2 at node 1. And at node 2, we can consider a body of weight LAF by 2. This is node 1, this is node 2. This is how we can understand. The entire weight of the elastic solid is equally shared by both the nodes. That is what we can understand. So very, very important. What is the expression for the element body force vector? It is a column matrix. It is a column matrix having the elements ALF by 2 and ALF by 2. It is a 2 by 1 matrix. Understand? Now we shall see element traction vector. Surface traction. Surface traction we can consider as another external force. Okay. Therefore, the work potential due to surface traction we have to determine. Work potential is always negative due to the external forces. Hence, I can consider here the work potential negative. Whether you put minus here or lateral, you consider doesn't matter. So, what is the expression? The expression for the work done by the surface traction is integral of U transpose T into dx. Okay, when you consider the entire solid, it is integral over the length of the solid. When you take the finite element, then it becomes integral over the length of the element U transpose, this is U transpose T into dx. What is T here? It is the surface traction. It is considered as I said, it is considered as force distributed per unit length. If you take an elastic solid of uniform cross section like this, surface traction is applied like this on the surface. Okay. Therefore, what is the respect to surface area? Length of the solid into perimeter of the section. So, what is the perimeter of the section? If d is the diameter, pi d is the perimeter, and the surface area is simply pi dl. But the perimeter pi d is same throughout the length of the solid. Therefore, you can define the surface traction as the force distributed per unit length. It is constant for each finite element, but it varies within the element. It is constant for each finite element, but it varies within the element. Okay. Now, the surface traction multiplied by the displacement. You get the work done. How you get the surface traction? Surface traction per unit length, T into the length of the element. So when you take an infinitesimal element, of thickness dx, distant x units from fixed support. Okay, what is the traction acting on the surface of this infinitesimal element? It is simply T into dx. Therefore, T dx represents the traction acting on the infinitesimal element. Right? If you want for the entire solid, you have to integrate. Okay. Therefore, U transpose T into dx. This is the expression. Integral over the length of the element for the element traction. Length of the element. Okay. Now, integral over the length of the element. When you consider an element. Integral over the length of the element, U transpose T into dx equals to, again, we know that U equals to N1 Q1 plus N2 Q2. Hence, integral over the length of the element N1 Q1 plus N2 Q2 into T dx. Right? Now, this, this we can split into the product of two matrices. What we can split? N1 Q1 plus N2 Q2. N1 Q1 plus N2 Q2. How you split? Again. Say here, it is written as a row matrix having the elements N1, N2 into a column matrix having the elements Q1, Q2. Okay. This is split into the product of two matrices. Understand? Right. Now, so here, because it is U transpose is same as U, but when you express U as the product of two matrices, N and Q, this I represent by N and this I represent by Q, then U transpose equals to Q transpose into N transpose. Then Q transpose becomes, a row matrix, and N transpose becomes a column matrix. Understand? Right. This Q transpose is constant. It comes out into T is constant. T lies. Now, integral over the length of the element N1 dx. Integral over the length of the element N1 dx. And again, T into integral over the length of the element N2 dx. Okay. So here again we know that integral of N1 dx, it is L by 2. Integral of N2 dx, it is also L by 2. Understand? Hence, how you get this matrix? We get this matrix as, say, Q transpose into, T is constant, so T into, okay. And here, integral of N1 dx, we know that LE by 2. Integral of N2 dx, we know that LE by 2, therefore T into LE by 2. This is how you get, right? This entire, expression you get like this. This entire expression you get like this. Q transpose into T LE by 2. Here T LE by 2. We have a column matrix. Understand? These two correspond to the degrees of freedom 1 and 2. Okay. Now, this TLE by 2, if you take outside, then how you get? You get the expression TLE by 2 into a column matrix having the elements 1 and 1. Okay? Now, this, I compare with the form. How? Say, Q transpose into some bracketed term. That bracketed term, I write element traction vector TE. Element traction vector TE. Element traction vector TE equals to TLE by 2 into a column matrix having elements 1 and 1. When I write this as a Q transpose into some bracketed term, that bracketed term I said element traction vector, which equals TLE by 2 into a column matrix having the elements 1 and 2. What we can understand from this? That is the question. Okay? Now, so what is the traction on the element? The traction on the element is simply T into L, length of the element. What is T? It is the force per unit length. Therefore, what is the total traction? TL. Right? This TL is halved because this TL is equally shared by both the nodes. If you have a one-dimensional element connecting two nodes like this, a one-dimensional element connecting two nodes like this, and this is the traction T, force per unit length, connecting two nodes, say 1 and 2. What is the traction on the element? Simply T into length of the element, LE, TLE. This TLE is equally shared by both the nodes. So, at node 1, TLE by 2 we have to consider, at node 2, TLE by 2 we have to consider. Understand? So, this is how one can derive the element traction vector. TE equals to TLE by 2 into a column matrix with elements 1 and 1. Right? Now, so we know what is element stiffness matrix. We know what is element body force vector. We also know what is element traction vector. Element stiffness matrix results from element strain energy term. Element body force vector results from work potential due to body force. Element traction vector results from the work potential due to traction force. Right? Okay. Now, I told you when there are 10 elements in the domain, for each element you have determined all these matrices. For each element you have determined element stiffness matrix. For each element you have determined element body force vector. For each element you have determined element traction vector. Okay? Right. Now, once you determine the element stiffness matrix for each element, assemble them, then you get a stiffness matrix, what is called global stiffness matrix. Global stiffness matrix, which represents the stiffness matrix of the entire domain. If the structure represents a domain, or if the domain is represented by a structure, the global stiffness matrix represents the stiffness matrix of the structure. Right? It represents the stiffness matrix of the structure. What it is? It is the global stiffness matrix. So, how you assemble all the element stiffness matrices after determining the element stiffness matrix for each element? That we see now. Okay. Now, I take a one-dimensional solid like this. I take a one-dimensional solid like this with single step. I can say a stepped bar. I can say a stepped bar. Right? This stepped bar is subjected to a tensile force F. Now, this has two parts. First part and second part. In first part, the cross-sectional area is same from here to here. In the second part of the solid, the cross-sectional area is same from here to here. Therefore, for this part, I say the cross-sectional area A1, length is L1. And for this part, the cross-sectional area is A2 and length is L2. Assume that the bar is made of same material. Therefore, Young's modulus is same for the entire material. Okay. Now, I implement finite element method. How many elements you can take here? A minimum of 2. From here to here I take one element, from here to here I take another element. Therefore, this is element 1 and this is element 2. How many nodes we observe? We can locate one node here, 1, another node here, say 2. This is the third node. It is a 3-node finite element model. It is a 3-node finite element model. This is node 1, this is node 2, and this is node 3. Okay. It is a 3-node finite element model. Now, what is my interest? My interest is here to determine stiffness matrix for each element. Then I prepare the stiffness matrices of both, then I assemble the stiffness matrices of both elements to have the global stiffness matrix. That is the stiffness matrix of the entire domain. Okay. Now for first element, here element numbers are answered. For first element, I prepare the element stiffness matrix. How I get? The element stiffness matrix of the first element, say K1 equals to, what is the formula? EA by L. Young's modulus is same for both elements. Therefore, E A1 by L1 into a 2 by 2 matrix having elements 1, minus 1, minus 1, plus 1. Okay. Now here these elements correspond to the degrees of freedom 1 and 2. Hence, I write 1, 2, 1. Remember, this is the first node of the first element, this is the second node of first element. Element connectivity information I am giving. Otherwise, you can prepare the element connectivity table. Element number, is encircled. Element number, next first node, next second node. E indicates element number. For first element, what is first node? 1. What is second node? 2. This is how I am taking. And for second element, what is first node? 2. And what is second node? 3. For second element, node 2 is first node and node 3 is second. Remember, for first element, node 1 is first node, node 2 is second node. For element 1, node 1 is first node, node 2 is second node. For element 2, node 2 is first node and node 3 is second node. That is what I understand from this table. From this table, that is what I can understand. Okay, this we say element connectivity table. Very, very important. Very, very important. Right? Now, after preparing K1, tell me these elements correspond to first and second degrees of freedom. Next. For second element, prepare element stiffness matrix. This equals to, again, what is the formula? EA by L. Hence, EA2 by L2 into a 2 by 2 matrix having the elements 1, minus 1, minus 1, 1. These correspond to the degrees of freedom 2 and 3. Hence, I write 2, 3 here, 2, 3 here. Now, you have to assemble both. You have to assemble both. Okay, ma'am? So, how you assemble? When you assemble, you get a global stiffness matrix that I denote by capital K. Its size equals the degrees of freedom of the domain. Here, element stiffness matrix size, if you observe, its size equals the degrees of freedom of the element, because there are only 2 degrees of freedom in the element. Right? The size of the element stiffness matrix is 2 by 2. Because there are only 2 degrees of freedom in the one-dimensional finite element. The size of the element stiffness matrix is 2 by 2. When you assemble all the element stiffness matrices, you get a global stiffness matrix capital K. Then its size equals the degrees of freedom of the domain. How many degrees of freedom are there in the domain? This is 1 degree of freedom, Q1, capital Q1. This is another degree of freedom, capital Q2. This is the 3rd degree of freedom, capital Q2. Therefore, you get the size of capital K 3 by 3. Okay. Hence, what I do is, I write this K1 like this. I write this K1. K1 equals to, observe carefully. Now, I write E A1 by L1 minus E A1 by L1 E A1 by L1 E A1 by L1. Here minus. Right? And I put zeros here. Zeros. I make this matrix into a 3 by 3. Okay? And see here, what are the degrees of freedom? Say 1, 2, 3, 1, 2, 3. I hope you don't have any problem. This matrix is written like this. There is no degree of freedom 3 here. Even though there is a degree of freedom 3 introduced, corresponding elements are zeros. I don't have any problem. This matrix can be written like this. Now, this matrix, how you write? I write here. Now, K2 equals to a 3 by 3 matrix. Now here, 0, 0, 0. I write here. Now, 0. Now, E A2 by L2. Next, minus E A2 by L2. Here minus E A2 by L2. Next here E A2 by L2 and here 0. What are the degrees of freedom here? Observe carefully. 1, 2, 3, 1, 2, 3. Right? So because there is no degree of freedom pertaining to node 1. Corresponding to node 1, I put the element zeros. Therefore, my matrix K2 is correct. This is written like this. Okay? Now, how you get the global stiffness matrix? Simply sum of these two. You get capital K. Capital K is simply a matrix of size 3 by 3. Right? Sum up simply. What you get? E A1 by L1. Next, minus E A1 by L1. Next, 0. Marla. Tell me. Minus E A1 by L1. Next, E A1 by L1 plus E A2 by L2. Next, minus E A2 by L2. Next, what do you get? So here, you get 0. Next, minus E A2 by L2. minus E A2 by L. What are the degrees of freedom? 1, 2, 3, 1, 2, right? This is the global stiffness matrix, global. Hence I use capital K. For element stiffness matrix I use small. This is the global stiffness matrix which represents the stiffness matrix of the entire domain. What is its size? Its size equals the total degrees of freedom of the domain. How many degrees of freedom are there in the domain? 3. Okay na? Right. This is how we prepare the global stiffness matrix for any domain. What we have learned in this particular class? Now we have learned about the body force vector, the element traction vector, and we also learned how all element stiffness matrices are assembled to have the global stiffness matrix, from which come the element body force vector results. The element body force vector results from the work potential due to body force. From which term the element traction vector results? It results from the work potential due to traction. Work potential due to traction. And how you prepare the global stiffness matrix? The global stiffness matrix is prepared assembling all the element stiffness matrices. Okay. Thank you. Thank you very much.